Okay, in this case, I don't care what this says. Automatically, I have to must simplify f of x equals 2 minus the absolute value of x over 2 plus x completely without absolute value. So no matter what the limit says, I cannot plug in anything, I cannot do anything before I fully simplify the function without the absolute value. And this is the more difficult than calculating the limit. But this is crucial and it's a very important step. Okay, so let's review. I don't have enough room here, so I'm going to move on to the next page. So let's review the absolute value definition. The definition of the formal definition of the absolute value. Formal definition of the absolute value. So the absolute value of x, what does it equal to without absolute value? Anyone?
Positive negative x.
Very good. Very important. If what?
If it's not equal to 0.
If x is greater than or equal to 0, and if x is less than 0. So now, what you need to remember is not this. You need to remember this. And you can say, okay, what are you telling us here? What is this? This means the following. If I have here any expression, if I have here x minus 1, for example, then I have here x minus 1, x minus 1, x minus 1, x minus 1. If I have, let's say, 3x minus 2, then I have 3x minus 2 here, and 3x minus 2 here, and 3x minus 2 here, and 3x minus 2 here. This is how I have to remember the formal definition of the absolute value. So we chose a simple example in which this was not 3x minus 2, but this is exactly plain x. Okay, so this is our starting point. So we will write the absolute value again, because that was the discussion. So we have x for x greater than or equal to 0, negative x for x less than 0. This is not what we are interested in. Our function is this. If this piece has two options, how many options will this piece have? Will the whole thing have? If the absolute value of x has two options, how many options will the whole function have?
2.
Of course. It was a silly question. Thank you. Thank you for not saying it was silly. Good. So let's see what the two options are. Can anyone, without simplifying anything, give us the first option?
It would be the function without the absolute value.
Yes. So when x is positive, then there is no need for the absolute value, and I will have 2 minus x over 2 plus x. Awesome. So now I have to be careful here. When is this function undefined?
Negative 2.
Good. Perfect. The denominator will be 0 when x is negative 2. So This -2 is not in this interval, so I have x greater than or equal to 0. And now let's analyze the second option for less than 0 but not -2. Careful. So here I have x less than 0, comma, not -2. What is the other option? Anyone wants to give it a shot?
2 plus x over 2 plus x.
Excellent. Since I already excluded that, this 2 plus x over 2 plus x would become what?
1.
Exactly. So the fully simplified form is then 2 minus x over 2 plus x for x greater than or equal to 0, and 1 for x less than 0 but not -2. Ah, good. So now, look what they want. They want the limit from the left and the limit from the right, or the limit directly from either side. So, perfect. Which branch do I use? I can only use one in this case. So the limit of 2 minus the absolute value of x over 2 plus x when x approaches -2 from either side is limit as x approaches -2 from what?
1.
Yes. And what is the answer? This is a limit law. The limit of exactly. Who cares where x is going to? 1 will always be 1. Excellent. Any questions? Any questions? Are we okay with the absolute value?
What happened to the 2 minus x over 2 plus x?
Who cares? We are asked to find the limit as x approaches -2 from either side. Can I use, if the limit is from the either side of -2, can I use this expression when this exists when x is greater than or equal to 0?
No.
No. So the question was only this. As x approaches -2 from either side, but I can't do anything before see, if you don't simplify this function, actually it's a very good question. If you don't simplify this function, you just plug in -2, you will get 0 over 0. And what do you do next? Nothing. You can't do anything. You don't know what it is. So even from the beginning, you could plug it in. So the numerator is 0, the denominator is 0. And now what? This is none of the previous situations. You can simplify, you can factor, you cannot rationalize. Squeeze theorem doesn't work. Nothing works. But now if you simplify the function step by step, then you realize what the limit is all about. So the limit is about this expression, which is this expression basically, as x approaches -2 from either side. So this doesn't even come into play because x approaches -2 from either side. This is the only way. Any questions? Okay, I would like to move on to the only proof that we are going to look at this semester. The precise definition of the limit, also called the epsilon delta definition. So we either call it the precise definition of the limit, or we call it the epsilon delta definition of the limit. Okay, what does it mean? First, let's try to understand what it means, and then I will repeat it several times, and you will understand it. It's very simple. More words than it needs, so it will look confusing at first. Okay, so let's suppose we have a polynomial function, f of x. Of course, our best friend, little a. Of course, our second best friend, uppercase L. From my graph, would you agree that the limit of f of x as x approaches a from either side is L?
Yes.
Yeah. I would like, because you've noticed I like not to write so much. It's not a lazy thing, but I like us to at least try to understand 4 symbols, mathematical symbols. I didn't make them up. You are not forced to use them if you don't want to. This upside down A translates into for every, or for all, or for any. The upside down uppercase A. This symbol, the backwards E, stands for there exists. Or I will find. This little E backwards, but circular E, stands for such as. Okay? Okay, so keep this in mind. I'm going to get to them in a minute. Let's assume I zoom in. I have this function, I have A, I have L, and I zoom in. And I zoom in, and I zoom in, and I zoom in if you want. So when I look at that, here's my L. And I zoom in, and I can find any time I want, zooming in or not, getting closer and closer to L, it doesn't matter. But I will always be able to find a symmetric interval. And this piece is the epsilon in the definition. So obviously this point at the top of the interval, this point here, will be L plus epsilon. And of course, epsilon is a tiny positive number, not 0. And it has to be positive. And this bottom part of the interval, that end point of the interval at the bottom, is of course it's L minus epsilon. Because this distance is epsilon, and also this distance is epsilon. So I have the function here. And notice that for every epsilon, so if it is zoomed in and it's very tiny, or zoomed out, it doesn't matter. For any epsilon, I will be able to find, drawing horizontal lines, and of course this is the L and this is the A, I will always be able to find an interval, a corresponding interval around A. Why is that? Because the limit exists. If the limit doesn't exist, it's a different story. But the limit exists. So if I pick epsilon very tiny, very close, I will still be able to find an interval around A. If I use a bigger epsilon, I will still be able to find an interval around A, no matter what. So again, because the limit exists. So that's the start of the definition. This limit exists means that for every epsilon, I'm going to put it in writing in a minute, for every epsilon around L, there exists, I will be able to find a delta. So for every epsilon, I will be able to find a delta around A such that, sorry about that, such that, now I have to stop for a second because we always have to choose the smallest distance. I cannot choose this because it's longer. I have to choose the smallest. Delta, always the minimum distance, always. And now I have to continue. And I'm going to find the interval. I'm going to say this is the interval. And I'll explain why it has to be the minimum. I promise. So this is the delta, and this is the delta. Of course, this point here at the lower end is A minus delta. Of course, the upper is of course, A plus delta. So let's repeat, and I'll come back to explain this in a minute. For every epsilon positive near L, I will always find a corresponding delta near A, also positive, such that when I pick X anywhere between this point and this point, so let's say whenever I pick X here, distance between X and A, this is the way we present distance, less than delta. So X is not here. X is not here. No, no, no. X has to be with a smaller distance than delta, either on this side or on this side, but the distance between A and X, or X and A, has to be smaller than delta. Every time I pick X within delta away from A, its corresponding f of X will be at a smaller distance from L than epsilon. I know it sounds confusing. I will repeat it several times and then we put it in writing. It's very simple.